So we had a small glitch with the audio-video system, but in the break, so we hope everything is fine again. So everything has been rebooted. It's what you do when something fails. So it's a great pleasure to introduce the next speaker, Professor Frank Piessens from Department of Computer Science, and he will give you an introduction to software security.
Thank you, Bart. Welcome to this introductory lecture on software security. It's really introductory, but I'm happy to take any questions you have, even if they go far beyond introductory. We'll see where we get. I'm happy to be interrupted. I'm happy if you want to ask questions or make comments during the talk. We'll see where we get. When you do this kind of introductory talk on software security, there are two directions you can take. Either you pick a specific sub-area and then you can get a certain level of technical depth. For example, I could focus on buffer overflows and then we can go relatively deep, but you don't have the overview of what of everything that matters to software security and how it fits in, let's say, cybersecurity as a bigger discipline. Or alternatively, you can go broad. You can start from cybersecurity and try to explain where software matters and what aspects of software matter to security, but at the price of not being able to go deep, right? So for today, I've chosen the second path. So it won't be technically deep, it'll be a broad overview, but I'm happy to go deeper in any of the aspects that I touch. So this is my home area, this is what I know, this is what I do research on. So it's hard to judge how deep to go on an introductory talk. So I'll go broad, but don't hesitate to ask questions. So given the goal of starting broad, this is kind of the structure of the talk. The introduction will actually take approximately half of the talk. I'll start from concepts that matter in cybersecurity and then try to specialize them to software and then focus on one particular, what I'll call control, that matters to software that is typically called software security in the most narrow interpretation of the term. And software security in that interpretation of the term is about software vulnerabilities, how to exploit them and how to defend against them. And so that will then be the second part of the talk. So from here onwards, we'll look at in breadth, at some examples of important classes of software vulnerabilities, how you attack them and how you defend against them. That's a bit the plan for today. Okay? So let's start broad. So what I'll do is I'll start by introducing a number of concepts that matter to security in general, not just software security, actually even security beyond computer security, even though I'll focus on computer security, on a concept diagram that I'll gradually build up, and then we'll see how to specialize this to software security. Okay, so what you see on the slide now are like the three core concepts of security. One thing you'll need are assets. Assets are things of value. You need to identify what in the system that you're studying has value to someone. If there's nothing of value, you don't have a security problem. There's nothing to protect, right? There must be something of value. The second question is, who cares about these assets? And that's what I call the owners and defenders here. And we'll see that you typically have multiple stakeholders and they may have different opinions about the value of these assets and they may even have different protection requirements on them. I'll give an example in a minute, right? So it's important to get an understanding of who cares about these assets, who are the owners and defenders. And the third thing you need are these attackers and threat agents. Who is out for your assets? Who wants to abuse them, damage them, steal them, right? If there's no adversary, you don't have a security problem. You might still have a reliability problem. You might care about things like flooding and natural disasters and earthquakes and that they can't damage your assets. But that's different. In security, we worry about an intelligent, strategic adversary that understands your system and comes up with intelligent plans to bypass whatever you do to protect your assets. So if you don't have attackers, I don't consider it a security problem anymore. So let's look at some examples, just to make this a bit more concrete. I'll look at the messaging system, something like email, WhatsApp. It doesn't matter. It's at a relatively high level of abstraction. So what would be assets there? Well, what you would expect, right? So the contents of messages you send, metadata about them, who are you communicating with? It's metadata, and you might not want everybody to know, for example, who you are communicating with. The contact lists that you maintain on your client device. The service itself may be an asset. The fact that you can send the messages is of value to some stakeholders. The infrastructure on which this runs, the network, the hardware, the client, the service, and so forth. Yeah? So these are actually typical assets for a computer security setting. You have information, services, and hardware or infrastructure. These are typically the three big classes of assets that you have to protect. Who are the owners and defenders in this example? Well, as you see, there are different kinds. So clearly, for instance, for messages, the platform users will care about them, right? So you may care about protecting the confidentiality or integrity of messages you send. The messaging platform provider, of course, might care, for example, about the service running. The infrastructure provider might care about network bandwidth, might care about the hardware, that it doesn't get damaged. So as an example of conflicting protection requirements, think about content of messages, for example. You can imagine that platform users want to hide content of their messages to the platform provider, or to WhatsApp, let's say. But on the other hand, you can imagine that WhatsApp might want to look into your messages, for example, to detect when you are doing illegal stuff on the platform. Right? So that's a clear example of a conflicting requirement. One stakeholder for security wants to be able to look into something, and the other for security or privacy wants to shield it. Right? So, and that's typical in security, that you'll have these conflicting requirements. And finally, attackers in this setting, again, this is an open-ended list, but you can come up with some examples. So for messaging, typically your close social circle, I mean your partner, your employer might want to see what you're doing, and you may want to protect against that. But at a very different scale, intelligence services might want to kind of do surveillance on a big set of users. Criminals might want to learn about you to do identity theft, or to more easily phish you or scam you. You could even say advertisement providers. Are they adversaries? I don't know, but they might want to learn about you to do more targeted advertising and so forth. Okay, I hope that clarifies these basic concepts. Now, of course, in computer security, and then we'll zoom into software security. In computer security, we're mainly interested in understanding how the presence of computer systems in the overall system change the risk to these assets. What's the influence? And in the messaging system, almost everything is on the computer, but you also have systems, I think in an industrial control system, for example, you also have a lot of physical non-computer stuff, and the computer is only part of the system. And in computer security, we're interested in understanding how the computer systems that are part of the overall system influence risk to assets. There are two key concepts in understanding that risk. There are things that increase risk, and there are things that reduce risk. The things that increase risk, we'll call them threats or attacks. Threat and attack, I'll use it as a synonym, but typically it's used. A threat is more a potential thing, a potential scenario that an attacker could do to damage your assets, whereas an attack is a concrete, actual scenario. But they're both scenarios that an attacker could perform to kind of abuse, steal, or damage your assets. And so the more scenarios you can think of, the more threats you can think of that the attackers you care about get to your assets, the higher the risk. Okay? So understanding what possible attacks are is important to understand what contributes to risk. So part of risk analysis will be understanding what feasible attacks are. On the flip side, how do you reduce risk? I'll use the term control for that. Security is, from a point of view of terminology, a disaster. People use different terms for the same thing. So you might see terms like objective, security objective, or policy or so for that. That means almost the same thing. I'll use control. Control is anything that the defenders or the owners of the assets do to reduce risk. Right? So any measure you take to reduce risk, we'll call it a control. And I'll give examples in a minute. Right? So they're in a sense the flip side of attacks. Right? So let's look at some examples in the messaging system. So what are potential attack scenarios? So attackers might eavesdrop on messages. They might spoof messages, for example, to phish you. They might use the messaging platform to send unsolicited mass messaging, like spamming. They might use the messaging system to spread malware as attachments, and so forth and so forth. I think you can come up yourself with many more attack scenarios. And any of these things, of course, potentially increase the risk to one of the assets we discussed before. What are controls that a defender could take? Well, protecting message confidentiality, and that can be done using a variety of mechanisms. I'll come back to that. Authenticating users, so making sure that people can't lie about who they are. Increasing user awareness is a good example of a non-technical control. Controls don't have to be technical. So by making people aware of the threat of phishing, for example, you may reduce the risk that phishing actually leads to financial loss. The controls certainly don't have to be technical. You could do spam detection, you could do virus scanning of attachment, all kinds of things you can do. All of these are controls. Make sense? Interrupt me if you disagree with something or if something is unclear. Two final concepts. So once you have looked at attacks and controls for your system, it's interesting to understand what in the system contributes to this attack or this control. What in the computer system, in this case, for computer security, what aspect of the system enables an attack, or what aspect or part of the system realizes a control? And so for the attack, we'll call that the aspect of the system that enables an attack, that turns a potential threat into an actual attack that could happen. We'll call that a vulnerability. And so again, that's a very general term. A vulnerability is any aspect of the system that enables an attack. And again, the flip side on controls are what I'll call security mechanisms. So a security mechanism is what you do in the system to realize a certain control. Again, I'll give examples right away. So for vulnerabilities, the use of weak passwords would be a vulnerability. It's an aspect of the system. It's something in the system that makes it possible, for example, for somebody to get to your messages by pretending to be you. Unprotected communication lines over which these messages are sent is an aspect of the system that might make it possible to sniff on these communication lines for one of the attackers that we looked at. So it's a vulnerability. Again, vulnerabilities can be non-technical. I'll focus in this talk mainly on technical vulnerabilities, but so the fact that users are gullible, are easy to mislead, is also an aspect of the system if you consider users as part of the system. And so that's also, you can also see that as a vulnerability, and in a sense, doing things like user training and awareness is then something that a control or a mechanism that tries to reduce that vulnerability. Similarly, for mechanisms, I think you can imagine, so for instance, for protection of message confidentiality, you could use cryptography during communication or access control during storage, for example. You could use a variety of mechanisms for authentication. You probably covered some already in earlier lectures in this course. You could do user training to work on the awareness of users, and so forth and so forth. Okay, so these are the key concepts that I'll need in the remainder of the talk. So then an interesting question is, where does software security fit in? I think if you hear this discussion of computer security, it's very broad. You want to keep risk to assets below an acceptable level, and we use controls for that, but they can be technical, economical, legal. To give an example of an economical control, to fight spam, if you make people pay a bit for messages, spam will go down. That's purely an economical measure. Legal, if you make spreading of malware punishable with sentences in prison, spreading of malware will go down. So that's a legal control. So controls can be very broad. And in a sense, the field of security engineering is understanding, for the given system that you're looking at, all the concepts that you see on this concept diagram. So you'll try to do risk analysis, attack modeling, security analysis, which is trying to check whether the controls you have are sufficient to deal with the attacks that you identified. You might do attacker modeling to understand who you're up against and so forth. So that's the broad field of security engineering, does all these things. And software security, that we'll come to now, is only a part of this. And any of the very specific technical security topics that you look at is only, in a sense, a small part of this big security problem. So let's look at software security. So one way, a very broad way to define software security is that you take the concept diagram we had and you specialize it to sub-parts of the system that are software-based. So you focus on some specific software subsystem, in the messaging system, say the client or the server, or some component in the client or the server. And then you try to understand how controls and attacks matter to that specific software component. Right? So, and at that level of abstraction, at that level of detail, you can think of controls as specifications of how the software component should behave. It should do this and that. And you can think of attacks or threats as things that should not be possible with that specific software component. Right? And that's one broad definition of software security, is that it is about software-related controls and attacks, and understanding what the mechanisms are to implement these controls, and understanding what the vulnerabilities are that enable these attacks. That's a broad interpretation, but it's a sensible interpretation, because this is really all the security aspects of software. We'll see later that in the literature and in many things you read, there are also more narrow interpretations of the term software security that make sense, but we'll come to that in a minute. So let me first look at this broad definition. An important thing there to say is that, as in all fields in security, part of the reason why this gets complicated, and we'll see it gets a bit complicated, is the fact that you're up against this intelligent adversary. So there is no notion of security that's permanent or time independent, right? If you're secure today, you won't be secure tomorrow. Why? Because attackers will come up with new attacks, new scenarios that you haven't thought of yet. And so you'll need new controls to deal with these attacks. And this is, and when you have these new controls, the attacker will again come with new attacks. That's what is called the attacker-defender race. You have it in all areas of security. It's very, very visible in software security. And that is what makes the field difficult and dynamic and interesting, right? So what I want to do now is look at a couple of these controls and attacks that are relevant. So this is now software security in the broad interpretation, and we'll zoom into the narrow interpretation later. So I'll look at some controls that are relevant for almost any software-based system. So, and I'll look at 4 controls: isolation, authentication, authorization, and implementation correctness. And I'll briefly explain on one slide for each of them what the control is, what the mechanisms are that implement that control, and what typical attacks and vulnerabilities are, right? So in order to do that in general, I'll use a very generic model of the system. I'll think about a software system that, I'll call it the protected system here. I'll think about a system that accepts requests and sends back responses to what I'll call subjects. So you can think of these as users, but it could also be other machines or other software components. I'll use the general terms subject. So this is, of course, extremely general. It applies to a ton of systems, but we'll see that all of the controls I'll talk about also will matter for all these systems. And so you can pick actually whatever system you know best. So here are some examples that fit this pattern. A web shop where the subjects would be customers and the requests and responses would be HTTP requests and HTTP responses, for example, where you put something in your shopping cart or check out and pay and so forth. Yeah. Or it could be an intranet, and then the subjects would be hosts on the internet that send packets or set up TCP/IP connections and do network-level requests and responses. Or it could be an operating system kernel where the subjects would then be processes and the requests and responses would be system calls and return values from system calls. Or it could be a database, or it could be even a physical system like an ATM and so forth. So anything I say on the generic controls will matter to any of these systems. So it's okay to keep one of them in mind, one that you know well, and then see how each of the controls that I'll talk about matter to that specific system. Okay, so let's look at 4 of these controls. The first one is isolation. And what is isolation? Isolation says, well, okay, you have this protected system. You think of it as handling requests and sending responses. Let's make sure that this is the only way to interact with the system, even for attackers. That's isolation, right? So if you want to think of the system as doing request responses over some well-specified communication channel, like HTTP or a TCP connection or whatever, let's make sure that's the only way to interact with the system. And you might think, yeah, That's kind of obvious, but it's not that easy to realize depending on how your software system is executed. So for example, if you think about a system running in the cloud, suppose your protected system is a VM that has a web server in it that deals with HTTP requests and responses, then you want to think of the system as just handling these HTTP requests and responses, but you have to be aware of the fact that on the same machine in the cloud, there might be other virtual machines belonging to other stakeholders, possibly attackers, and they might have ways to interact with your system in other ways, and if that's possible, that's always bad. So isolation is about ruling that out, or at least understanding what's happening there. Right? So another typical example where that matters is for protected systems that are under the control of the attacker. If your software runs on a smart card and the smart card is in the hands of the attacker, a smart card software is designed to handle APDUs, application protocol data units, requests to the card and responses, but the attacker might break the chip open, fire lasers, do all kinds of crazy things to extract secrets from the card, for example. So an isolation is the control that tries to deal with that risk. So what mechanisms are used? So remember, control is implemented with a mechanism that depends on how your software-based system is executed. So for example, if your software-based system is a process running on an operating system, you use things like virtual memory and privilege levels and so forth to isolate processes from one another. So there are hardware and software and operating system mechanisms to enforce that isolation. In the cloud, that would then be a hypervisor that does virtual machine isolation using similar mechanisms. Right? What are the attacks that matter here? So this is what are typically called side channel attacks or fault injection attacks. So for example, if one of these VMs here could learn about you, one of the ways it could learn is through how you both are interacting with the underlying computer. Right? So you might share some resources. Your system and the attacking system might share some resources on this host, and by monitoring those resources, maybe the attacker can learn something about what you're doing. That's a side channel attack. And similarly, a fault injection attack is one of these machines, or a physical attacker trying to inject some errors or some integrity violations into your system. What are the vulnerabilities that make this possible? Well, these are typically things like what I mentioned, resource sharing. A typical example is the cache. So the cache is a fast memory between processor and main memory, and might be shared between two VMs in the cloud, for example. If that's the case, by monitoring the cache, an attacker can learn what the protected system is doing. And that's a typical example of a side channel. And I think there will be later more advanced lectures in this course that go into that more deeply. So that's isolation. First control. Second control, authentication. Actually, I think you already had a lecture on that, so you know what this is. So authentication is, we know the system now only can be interacted with through these requests and responses. The next thing we want to know is, who do these requests come from, and who receives these responses? And this is a complicated field in itself. So even saying what the answer to this who question should it be a user ID, should it be an email address, should it be a machine ID, should it be an attribute of somebody, like you're a member of the CS department, is an interesting and difficult question to answer. But the general idea is you want to know who you're interacting with. And the mechanisms you use to do authentication depend on both what kind of thing you're trying to authenticate and over what channel you're trying to do it. And as a very simple example, if you're trying to check who a user is over a local trusted channel, like at your laptop, you could use things like a PIN, a password, and biometrics. If you want to check whether you're talking to the right machine over the internet, you'll use cryptographic protocols typically. And there will be other lectures in this course that go into the details of these protocols. But so these are the mechanisms you use to achieve authentication. And what are the attacks? Well, typical attacks against authentications are password guessing is the very easy one. Replay attacks is a typical attack against the cryptographic protocol. Maybe you'll come back to that in other lectures. For those who know about web security, cross-site request forgery is an example of an attack against authentication on the web. And what are the vulnerabilities? Well, they're kind of like obvious, like weak passwords or reuse of passwords among multiple sites might be a way that attackers can break authentication. But also protocol flaws and bugs, I guess, well, like Matti van Hoof spoke today, I guess he talked, among other things, about for instance, implementation bugs or design bugs in protocols. So my main goal here is to give you, to show you how broad this all is, so that you can better position some of the more detailed technical talks that other people will give in this course. Third, authorization. Once we know you can only interact with the system through requests and responses, we know who is sending these requests and receiving these responses. The next thing is, well, are they allowed to do what they're asking? So I get a request from A to do something. Is A allowed to do this? And that's typically, of course, something application specific. You need some kind of policy, some kind of specification of what is allowed and not. And depending on the policy, you will have different ways of different mechanisms of enforcing the policy. So the most typical example is access control. Access control policies say something about when a request comes in, is that request allowed to proceed, yes or no? For instance, on a social media system, somebody can request to see the timeline of a user if they're in a friend relationship with that user, which is a very simple example of an access control policy. The typical mechanism to implement that would be a runtime checks, a runtime monitor. So you will put something in the request handling flow that checks when a request comes in, whether that request is authorized according to the application-specific policy, and if so, allow it, and if not, drop it, or send back an error message. You can't always use this mechanism. You might have policies like this is an availability or liveness policy. A payment request should be handled within 2 seconds. You can't enforce that with a runtime check. You can't force something to go faster by having an additional check in the request flow. So here you might need mechanisms like analyzing the code that authorizes payments and see whether there are any places where it can get stuck and whether you don't have loops that could run too long and so forth. So the mechanism you would use here is maybe more analyzing static analysis of the code and so forth. Typical examples of attacks against authorization, an example from the web context, forceful browsing, where you try to bypass access control by messing with the URL. So you change something in the URL because then you hit a spot where the web server is not implementing this runtime check. Or confused deputy attacks, where you don't have access to something, but somebody else does, and you trick them into doing something on your behalf, so that you get what you want through some confused deputy, as it's called. And there are many more, and examples of vulnerabilities. So a typical one is incomplete mediation. So this is, you forget a check in one place, right? And that's what forceful browsing will exploit. So this attack, forceful browsing, is enabled by this vulnerability. But also, for instance, configuration mistakes in setting of the policy. You might have checks everywhere, so you have complete mediation, but you have a bug in your policy. Then clearly, again, people might bypass authorization. So an attack is possible and is enabled by this specific vulnerability. Okay, makes sense? Last control, and maybe somewhat more surprising or unexpected, is implementation correctness. So again, we are now in a situation where we know you can only interact with our protected system through requests and responses, and we know who they are coming from and where the responses are going. And we have checked that indeed the request that comes in is allowed by the application-specific policy. So now it can proceed. We can let the code that implements the request run. But of course, if that code contains bugs, we're still screwed, right? So that's what this control is about. How can we make sure that the code that we run when we dispatch a request that we have done all these checks for, how do we make sure it doesn't do anything else? And that could be stupid bugs, like it might be a read request, but the implementation writes. That's what people would call a logic flaw. But the surprising thing about software security is that you can have bugs that at first sight might seem relatively unharmful, but because of the existence of specific attack or exploitation techniques, they're actually quite bad, and attackers can, if you have a bug like that in your request handling code, the attackers can essentially take over your system, right? So these are what I call here these generic classes of software vulnerabilities that enable specific exploitation techniques, and that's what the narrow interpretation of software security will be about, and what I'll say a bit more in the next part of the slide. So to complete control mechanisms, attacks, and vulnerabilities for these classes of problems, depending on the implementation correctness issue that you will have different mitigation mechanisms. For instance, for a logic flaw, you would typically do testing, code review, verification. We'll look at mitigation mechanisms for these generic classes of software vulnerabilities later. The attacks are the specific exploitation techniques that I mentioned. We'll look at them later in more detail. Some of you may already know them. And the vulnerabilities are, in this case, of course, the underlying bugs. Remember, vulnerability is an aspect of the system that enables an attack. In this case, for example, for a memory management vulnerability, you will have some bug in your code that allows out-of-bounds memory access, for example, that will enable a buffer overflow attack. So the vulnerability is the underlying bug. Okay, so now we come to this more narrow definition of software security, and that's, I guess, also the more common interpretation, that software security is really about studying these classes of bugs that are so bad, right? So what kind of software vulnerabilities are there? What types are there? How do you exploit them? How do you prevent them? How do you detect them? How do you mitigate exploitation? How do you make exploitation harder? How can I provide assurance that these kinds of bugs are not in my system, and so forth? So that's the narrow interpretation of software security, the study of software vulnerabilities, and that's the focus I'll take from now on. Okay, but I hope you found it useful to see how it fits in the bigger picture, because there's a risk if I zoom into, let's say, just one of these classes of vulnerabilities immediately, that it's hard to connect it to overall cybersecurity. Okay, so that's first part is behind us. Maybe any questions so far, or comments or concerns? No, I don't know if that's a good sign or a bad sign. We'll see at the end. So let's zoom in then on the study of software vulnerabilities. What I'll do is I'll first try to convince you of the fact that they're common, they occur a lot, and that they're dangerous. And I'll do that by giving you a bit of empirical evidence, numbers, and some historical examples. So that's the introduction, and then we'll look at two classes of software vulnerabilities in more detail. So first, they're important. Why? Because they're common and they're dangerous. So for common, one piece of evidence is, in the US, you have an organization called MITRE that maintains a database of known vulnerabilities in widely used software and hardware. It's both software and hardware, but it's what, 80-20 software versus hardware. Here is their definition of what a vulnerability is, and if you read it, I'm not going to read it out, you'll see it closely aligns with what I call the vulnerability. It's some bug or some flaw of the system that allows specific attacks to occur that might break confidentiality, integrity, or availability. So this is a different definition, but it aligns with mine. And at the point where I made this slide a couple of months back, more than 200,000 vulnerabilities were on this list, were assigned an identifier by MITRE. So that is, I think, evidence that this is common, the fact that you have these bugs. They're not all dangerous, but some of them are really dangerous. And to give some examples to illustrate that, to provide evidence for that, I'll look at two historical examples. The first is Heartbleed. Heartbleed is an example of a memory management vulnerability that we'll, if we have time, look at in a bit more detail later on. The essence of the idea of a memory management vulnerability is in languages like C or C++, where you as a programmer are responsible for memory management. That means you allocate, deallocate, and access memory, and you have to do that according to certain rules. For example, if you allocate 100 bytes, you can only access these 100 bytes. You cannot access out of bounds. If you allocate, you have to deallocate. After the allocation, you can't access that blob of memory anymore. So you have a number of these rules. If you violate these, so in C, it's your responsibility as a programmer. If you violate these rules, you have a bug. These are memory management bugs. And some of them are very dangerous. And an example of such a bug was the Heartbleed bug. And I'll explain it on the slide here. So Heartbleed was a bug in OpenSSL, a library used to protect the communication, among others, between a browser and a web server. Part of that protocol was what the Heartbeat protocol. It's a very simple protocol that essentially allows a client to check whether the connection is still alive. So a client can send a heartbeat message and get back a heartbeat response. And when the client sends the heartbeat message, he sends along a payload that the server is supposed to send back in the response, right? And the client specifies both the payload and the length of the payload. And the bug, the heartbleed bug, was that the server did not verify that this length was correct before using it. That was the essence of the bug. So it's a very simple bug. So what the server did, so if the client lies, sends 9 bytes of payload, but says it's actually 65,000 bytes, then what the server does is it will load this payload in memory, right, in the server memory. Will then, when it's sending back a message, it used the incorrect length that was not checked by the client. So what the server does is it sends the 9 bytes, and then anything that happens to be next to these 9 bytes in memory. So that's why it's a memory management vulnerability. You're accessing memory out of bounds, essentially. And so essentially you're sending kind of a memory dump of a part of your memory to the client, and if you're unlucky, and there is interesting stuff in there, and in the case of Heartbleed, the private key of the server could be in there, and once the client knows the private key of the server, it's game over, right? So then he can impersonate the server, and you've essentially taken away a lot of the security of the web server. That's the basic idea of Heartbleed. So very simple bug, very, very grave consequences. And this is typical. So here's another example, my last one. Stage fright is again a memory management vulnerability in Android. Stage fright was discovered in 2015, and at the point where it was discovered, it was on more than 1 billion smartphones, right? So really widespread. At the point it was discovered, it was already in there for 5 years. So for 5 years long, about 1 billion devices were vulnerable, had this bug. The effect of the bug was, if you had this bug on your phone, somebody could send you a maliciously crafted message, a multimedia message, that would essentially make the attacker who sends the message take over your phone. Can make your phone do anything he wants, like turn it into a listening device, dump your contact list to him, read all the contents of your phone, and so forth. Right? So it essentially allowed attackers to take over the phone. Right? So this fact, the fact that a simple bug can make it possible that an attacker completely controls your system, is what makes software vulnerability so important. And that's why software security is sometimes just about that. That's why software vulnerabilities contribute so significantly to risk in this overall picture that I started with. This is what the security engineer will call an elevation of privilege, and what hackers will call hacking, exploiting, or pawning a system, kind of taking it over. Right? So let's try to understand later how that is possible. I'll try to give at least an essence of an idea of how this can happen. So the fact that these vulnerabilities are possible, that make it possible to break into a system, turns them actually into some kind of weapon, or maybe more correctly, a burglary tool. If you have a vulnerability that's not fixed, you can break into a system. And that's why zero-day vulnerabilities are so valuable today. A zero-day vulnerability, the 0 day comes from the number of days that the producer of the software knows about this vulnerability. So a zero-day vulnerability is a bug in a software system that the producer of the system doesn't know about yet. And that's actually really a burglary tool. You can use that to break into a system. Right? And that's why it's worth a lot of money. And if you find such a vulnerability, you can go to the company that produces the software. That's typically... They might have a bug bounty program where they pay you for finding such vulnerabilities. And you see here that, for instance, in 2022, Google paid out $12 million in bug bounties to people who did that. Alternatively, you can take your vulnerability to a company like Zerodium that turns them into actual weapons that then can be used to break into systems. And you may not be able to read this, but they pay up to $2 million for a high-profile vulnerability. Right? And then they say they sell this to law enforcement, but yeah, it's hard to check whether these are their only customers, of course. So in a sense that it's like selling weapons. On the other hand, so some of you will have heard about SkyECC. We don't know how the police in SkyECC took over the phones of these criminals. I don't have any technical information on that, but a likely explanation is that they exploited one of these vulnerabilities in the SkyECC software. Right? So it is used by law enforcement, but it's probably also used by criminals to break into systems. Okay, let's look at some examples, especially since this is an introduction and you may not have seen many examples of software vulnerabilities. I want to say something at least about the two most important classes of software vulnerabilities. One, which is relatively simple to understand, and I want to make sure that I get a simple example across completely, at least for this one. And then memory management vulnerabilities, because they're still by far the most important class. And then there are many more classes of vulnerabilities, but I'll give you pointers to find information about other examples. So what are structured output generation vulnerabilities? These are bugs in programs that generate structured output from strings. So the program gets strings, and some of these strings might come from a malicious user, an attacker, right? And tries to combine these strings into some well-structured output, typically another program. For example, you might take in strings and generate a SQL query. Or you might take in strings and generate JavaScript to be sent to a browser. Or you take in strings and you generate a command for the bash shell to do something on your system, right? So these are prototypical examples. So doing that, generating structured output by manipulating strings is extremely error-prone. It's very hard to get this right, especially if the attacker can choose the strings, the input strings arbitrarily. The attacker might be able to change the meaning of the structured output of the program you generate quite fundamentally. And I want to give you one example of that. It's an example in a web application context. So here you see the typical structure of a web application. Think Amazon, for example. Then you will have some JavaScript running in the browser and some HTML showing you what you're currently doing. You might be browsing products or putting stuff in a shopping cart or whatever. On the server side, you will have business logic running. So if you, for example, search for a product, there will be a piece of code here that takes your keywords, asks the database for all products that are related to that keyword, and sends back HTML to show you a list of products that you might be interested in. Right? So we have code running here, typically JavaScript code running here, and then a database that has all the persistent state. And the code here typically will interact with the database by this kind of structured output generation, by generating SQL queries to be sent to the database. So here is an example of a piece of code that might be in the middle tier here. Right? So what does this do? This could be part of the login functionality. So essentially what it does is it shows on the web browser side a form where you can type in a name and a password. And what this will do is it will generate a query to the database that looks like this. It will take this name, plug it in here, take this password, plug it in here, and this resulting thing is intended to be a query for the database that checks whether in the users table there is a row with this name-password combination. So even if you don't know SQL, I think you can understand more or less what this query does. It looks in the users table and it tries to find whether there is somebody with that name and password. And so the idea is if you get a row back here, if you get one result, it means this is a valid username-password pair and you can continue as N. If you don't get one back, you have error handling saying, oh, we don't know you, please make an account, or incorrect password, try again, or whatever. Right? That's the idea. So that looks at first sight as a reasonable implementation. Well, you can have all kinds of critique on it, but it has a very important structured output generation vulnerability. If the attacker can pick this name to be any combination of characters, for example, the attacker could pick the name to be this, right? Let's see what happens then. So the code will stupidly do what it's supposed to do, plug the name in here, plug the password in here to generate this as a structured output. But now what you see is, and that's the essence of a structured output generation vulnerability, the structure of the output will change. The quote that we had here, that we put as input in the name, now appears here and it terminates this quote. That was never the intention. Right? This should not be possible. That's a bug. Right? And then the dash dash that you have here is a SQL comment character, right? So that appears here, and it makes essentially the database ignore anything behind the dash dash. So now we have really changed the structure of the output. Rather than checking for a name and a password, now it's just checking for a name. And now this will return one row as soon as I get the name correct. So now as an attacker, as soon as I know a username, I can log in. I don't have to know the password anymore. And so if I know the admin username, I can log in as admin. right? So this is an example of how a very stupid bug can have disastrous consequences. And I think for this kind of code, I hope it's obvious that this works, right? Okay, so this is a small and stupid example. But this class of vulnerabilities is huge and is important, and it occurs beyond SQL. It's sometimes also called injection vulnerabilities and corresponding attacks, because what you typically do is you inject unintended code into the system. So you, for instance, inject an unintended additional SQL query into the system. And I already mentioned it can happen with SQL, it can happen with shell commands, it can happen with JavaScript, it can happen with HTML, it can happen with CSS, it can happen with all kinds of structured output, mainly the ones that can also cause some kind of effects that are useful to the attacker. Okay, so that's one category of vulnerabilities. Let's look at one other one. Memory management vulnerabilities. I already mentioned them briefly. So this is relevant to software in languages like C or C++, where you have to do your own memory management and where you have to make sure that you follow these rules that I mentioned before. So if you are in charge of managing memory, you have to make sure that you do it correctly. So if you don't do it correctly, you have these. You have what is called a memory management vulnerability, and then the question is what can go wrong. And the easiest way to understand what can go wrong is look at a very simple example. So here you see, this is kind of the simplest example of a buffer overflow attack I could come up with. So here you see the code of the program. It's a toy program. So what it does is it declares a string. In C, a string is an array of characters terminated with a null byte, so you terminate the string with a null at the end. So here you read the string, and then you have a variable here that you initialize with 0, never change, and if it's different from 0 at the end of the program, you print out you win. If you look at this program, you would expect the program never to print out you win, right? So this is the goal of the toy attacker is to make this program print out you win, despite the fact that, according to the program code, this should never happen. Right? And later, in a minute, we'll generalize. So in general, you should think of this. This is some good but buggy program, and the attacker is trying to make it do something that it normally wouldn't do. And this is the simplest case. So how is that possible? Well, if you look at the implementation of this method here, so the getString, which reads a string from standard input or a network socket, or whatever you choose. The way in which it's implemented, the essence of it is what you see here. Essentially what it does is it will read character by character until it reaches a new line, when you press enter on your standard input, for example. And then it will kind of write the null character to terminate the string, and then it has its work done. But you immediately see that this might lead to an invalid memory access, right? So the buffer here has only room for 10 characters. But this might go on as long as the attacker desires. As long as the attacker doesn't type a new line, new characters will be put in the buffer. And so the consequence is this buffer will be somewhere in memory, and you'll start filling it with characters. And when you reach the end of the 10 bytes, you just continue, and you continue as far as the attacker wants. And as a consequence, the attacker can change contents of memory a bit. And that possibility, the fact that you can change memory a bit, is disastrous. You can make all kinds of things go wrong. And so the simple thing here that you can do wrong is change the value of this variable C. If C is allocated closely to buffer, right, which could happen because they're declared together. So unless the compiler has certain countermeasures enabled, it's likely that it will happen. Then by overwriting the buffer, you might actually change the value of this variable too and make this actually print out you win. Does that make sense? Yeah. So of course, this sounds very academic and very not, I don't care like in practice. But of course, the point is that if you have a bug like that, it means you can change memory, and being able to change memory has disastrous consequences. So as a first example, I don't need to have this help for the attacker here in the program. I don't need to have this variable and this print you win in here. Here I have the same program simplified. I took out C and I took out the print you win. You can still make it print out you win. And that's already a bit scarier, but I guess many of you have seen that already. So there are many things you could do to make this printout you win. One of the things you could do, again, it won't work on modern systems because countermeasures are at work, but one thing you could do is, well, if you can overwrite memory, if you can change memory, maybe you can change the code because the code is in memory too. So the compiled code of this program will be somewhere in memory. If you can reach that area of memory with your buffer overflow or with the memory management bug that is there, you can change the code. That's called the code corruption attack. And then, of course, that new code that you wrote will execute, and you might put there code that prints you win. That's not the most typical way to exploit it, but it's possible. And you have many other options. So actually, there's a whole classification and a hierarchy of attacks that you can do if you have a memory management vulnerability. So a data-only attack is the first one. The first one we saw is an example of that, where you use your power to change stuff in memory, to change values of other variables, to make the program take a different flow and do something that was not expected. The second example I mentioned was this code corruption attack. You modify the compiled program. Yet something else you can do is what is called the control flow hijack attack. So you modify some code pointer, for example, a return address, some value that represents code in memory that the processor will jump to at some point. You modify that, and then you can make it jump somewhere else and put your own code there. That's called the code injection attack again then. And there are many more things you can do. The general rule of thumb is if you have a memory management vulnerability in your code, it's very likely that your code can be taken over to do anything the attacker wants. Okay? Okay. So let's see, I have a couple of minutes left to say something about countermeasures. I will mainly point you to literature on this. Clearly, given the risks with software vulnerabilities as we discussed, you might want to have some controls that reduce that risk. There are, roughly speaking, three things you can do. You can prevent the introduction of these kinds of bugs in your software. For a simple example, rather than using C, use Rust or use Java or use some memory use some language that takes the responsibility of memory management out of the hands of the programmer, and then you won't have these bugs. Right? Actually, the White House in the course of this year advised to no longer use C and C++ exactly for this reason. Right? So to just prevent these kinds of vulnerabilities entering into new software. You can detect these vulnerabilities, so you could say, okay, I have a lot of C code, I have a lot of C++ code, or I have SQL injection vulnerabilities in Java code that I have. Then you can use detection tools to find them and maybe remove them. And there is a lot of tool support for that. For example, for memory corruption, you have what are called sanitizers, which help you, so you compile and test your program in a way that will, when you have a memory management vulnerability, will more likely make the program crash. So that's a good way to test for the presence of these vulnerabilities, to detect them, and then maybe remove them. Right? Or the third thing you can do is, you can accept that you can't get rid of all of them, so they will be in your running system, and then what you can do is try to make exploitation harder. So you can do all kinds of measures, and modern compilers and modern operating systems and modern hardware provide a lot of support for that, to make it harder to exploit that vulnerability. For example, the code corruption attack that I mentioned is typically no longer possible today because the operating system will mark the code segment as read-only. So if you overwrite this buffer and try to write code, it will actually lead to an error rather than you changing the code. This may not be the case in embedded systems. In embedded systems, you may still have scenarios where you can do code corruption attacks, but on a typical modern, let's say, desktop or server system, this is an example of such a mitigation. So unfortunately, in the course of an introduction, I can't go into detail on all of these countermeasures, these controls. If you want to know more, both about the categories of vulnerabilities, I only discussed two, there are more, And about all these, if you want to have more details about all these controls, there's actually a freely available chapter of the cybersecurity body of knowledge. I put the URL in the slides, and I think you have access to the slides, that expands on this in like 20 to 30 pages, discusses each of the categories, discusses each of the countermeasures, and also provides pointers to more information. So if you're interested, that's a very good starting point to learn more. Okay, and that brings me to my conclusion for today. So I hope I convinced you at the start that, well, cybersecurity is a very broad field. We won't solve it with one kind of technical solution. It's not just crypto, it's not just hardware security, it's not just software security. It's a tricky, complex, interesting, interdisciplinary, broad field. Even if we look just at technical aspects, and even if you just look at technical aspects of software-based systems, you still have a variety of attacks and controls, and I discussed a wide range of them, like isolation and side channel attacks, authentication and spoofing attacks, and so forth and so forth. But then specifically for software, we have this potential of the presence of vulnerabilities that have corresponding exploitation techniques that can be really, really impactful and increase risk significantly. So that's what typically software security focuses on. What are these software vulnerabilities? How do you exploit them? How do you mitigate them? And there we discussed two, and I think the two most important categories at a very high level today. Okay, I think that finishes what I wanted to say. We have 3 minutes left for questions, I think. Any questions, comments, concerns? Yes? Yes, but it's growing fast. So I'm hopeful for Rust. So I think it's been the fastest growing and language in popularity and in use for years in a row. So I think it's growing, but of course a very important problem that remains is there's a huge amount of legacy code in C and C++ that people will not rewrite. It's just too expensive to rewrite, I think. I remember an experiment by Microsoft 20 or maybe more than 20 years ago. At the time they came with C#, which was also a potential replacement for C, but it less good than Rust, I think, because it's still at... and they did an attempt to rewrite part of their software in C# and gave up at some point because it was too expensive, and it was also impossible to get it to do exactly the same, right? So for instance, they tried to rewrite part of their Office suite. Doing that and making sure that all Word documents look exactly the same on the new version was just too expensive. It was infeasible, essentially. And I think you have the same problem now. So I think that there will be I don't think C and C++ will go away anytime soon, if only because of legacy issues. I do hope that for new developments, languages like Rust will play a much more prominent role. And I think there are indications that this will happen. But it'll take years, right? So don't think the problem of memory management vulnerabilities will go away in the next 20 years. That will not happen. Yeah, good point. So the question is, what is the relevance of CWE, the common weaknesses enumeration, rather in comparison to the common vulnerabilities and exposures? So what are the CWE? What are the common weaknesses enumeration? It's an attempt to put some structure on these 200,000 vulnerabilities. So clearly, some of them are very similar. So can we come up with some kind of systematic classification? That's what the CWE tries to do, and then it can also help you try to understand whether a countermeasure that's applicable for an entire category of vulnerabilities is applicable to a specific vulnerability and so forth. So I think it's a great initiative. I also think it has its flaws. In the 30 years that I've been in this field, I've seen several attempts at kind of coming up with this kind of classification, taxonomy of vulnerabilities. I actually was guilty of that myself. I tried to come up with one myself in the early days. Every time somebody does that, you end up with a different taxonomy. That's not a good sign, right? And I think the common weaknesses enumeration, there are many classifications that you can argue with. So I think it's good to try to get a better understanding of, you can't look at 200,000 vulnerabilities and learn something from it. So we need to find structure in it, we need to find, and this helps. I don't think it's the final word on how we should taxonomize vulnerability. It's actually a more general problem. How do you taxonomize bugs in software? That's also something people have tried in software engineering, and it's very hard, right? You can make mistakes in so many ways that it's hard to put a... I don't think there is a canonical structure. So in that sense, I think the CWE will always be an attempt, but it's not like a scientific final classification. Yeah. Other questions? Comments, concerns? If you disagree with anything I say, speak up. Not? If not, then I suggest we end here. Thanks a lot for your attention and enjoy your lunch.